Yes. So, yeah, let me repeat. Sorry. Let me repeat that I'm starting with the chapter 26. And, well, basically, I'm going to start describing Kirchhoff's circuit rule. So, um, the junction rule I have described earlier, so as a result, I'm not going to spend too much time on this, but we are going to say it like this. Basically, the sum of all currents, let me repeat everything that I have said, actually. So the sum of all currents that approach to a junction is equal to 0. So let's remember that when we assign a current variable, we always put an arrow on that branch and then express the current along that direction. And so as a result, some of these quantities can be negative. We just always keep this in mind. So I think one of the important things that I stress on this course is that any of these variables can be negative and there is nothing wrong with it, right? Because a lot of students actually try to assign variables in such a way that they always find positive current values. No, that's not necessary, right? So when you're writing down the, I don't know, the circuit equations, for example, you don't have to, I mean, you can use variables with negative values as well. No problem with this. There's no special difficulty in here. So we basically said that the sum of the currents approaching to a junction being equal to 0. The reason is that the charge at the junction or around the junction, this charge in here does not change with time. Well, it is 0, so therefore it doesn't change with time. So normally it should be 0. There can be a charge pileup temporarily, but in any case, I mean, this is not going to this is going to dissipate quickly, probably. And so as a result, for all practical purposes, we set this to be equal to 0, right? Again, it kind of, there is some kind of an approximation in there that you're somehow ignoring the charge pileup phenomenon at different parts of the circuit, but it is really negligible for the kinds of circuits that we are studying. So in any case, but a lot of you, of course, know this rule in this way. You basically say it like this: the sum of the incoming currents is equal to the sum of the outgoing currents. So outgoing. So that means if the current variables are I1 and I2, but this arrow is drawn like that, in the incoming ones, I have I1 plus I2, and in the outgoing ones, I have just I3. Okay, so that's okay, no problem with this. I mean, there's no particular way of we write these things down, but eventually, of course, when you write down the junction rule, you are going to have arrows in arbitrary directions. As a result, you always use this kind of arrow. Okay, let's just say it like this. Right? I'm not going to write this thing down. The other one is it's called the loop rule. This is the first time that I'm going to describe it. In any case, what happens is that we basically, I mean, let's just consider the circuit something like that. I'm not going to draw the resistors and things like this, all right? Let's say it like this. So there are some resistors perhaps in here. So that's a circuit perhaps. Let's say, I don't know, I mean, let's say that there are some EMF devices, resistors and things like that in here, right? And then you draw some kind of a loop, you follow a loop. So that means you start from some point and then come back to the same point again. So that's my loop in here. So that's the loop. And basically, basic idea in here is that the sum of the potential changes over a loop is equal to 0. And the reason is this, well, the potential change, right? Well, potential is a well-defined function. So the potential change is always of the form that it's basically the potential at a point minus potential at some other point. So as a result, in this kind of situation, we have like points on I don't know, the junctions or I don't know, some special points on the circuit. So let's call it as A, and this one as B, and this one as C, and so on. In any case, let's continue like that. Since all of the potential changes are like this, essentially we are going to have a situation where the potential change is like, the potential change on this branch is going to be VB minus VA. On this branch, it is VC minus VB, and so on. But in all of these cases, these variables cancel each other. So this VA would be, this VC would be canceled by something else in here, and so on. So as a result, at the end, all of the variables cancel and you get 0. All right, so in this kind of an expression, you basically have every point, the potential at every point is subtracted, and it is subtracted, yeah, whatever. It basically appears with both signs in the same equation. So as a result, all variables vanish, right? So let's say it like this. We can express this loop rule like that. This is the sum of potential differences on a loop is 0. Okay, again, just note the difference in here, the potential difference, potential drop. There's always an arrow that I follow in here. When I am following an arrow in here, I'm assuming that I'm walking along the arrow. So as a result, for example, on that branch, I'm essentially moving from A to B. And when I say the potential difference, this is always the final potential after moving that branch minus the initial potential. Okay, so that's basically what I mean by potential difference. Instead, I can write down the same expression in terms of the potential drops. So that's the sum of potential drops on a loop is 0. So that's the alternative way. What's the potential drop? Basically, potential drop is just the opposite of it, right? It's the initial minus the final potential. And the way I define it is like this. If the potential really drops, the value of the potential drop is basically positive, right? If it drops, then the drop is positive. If it doesn't drop, it just increases, then the drop is negative. So that's how we define it. Again, the direction that you go is important. So along the direction that you go, if the potential really drops, then this. So in any case, let me just do it like this. I think I'm going to use a circuit like that, right? So I have some kind of an EMF device in here. Let's say this is 3 volts. And I have some kind of a current in here. I don't know, let's just call this as, yeah, I think I'm going to call this as, this current as I1, whatever. In that branch, let's say, there's other branch in here. So this is the resistor R2, and this is I2, and so on. So I think I'm going to have one more EMF in here. Yeah, let me just forget about these values. So I think that the values are not important in here. Okay, so that's the example. So as a result, let's say that this is my initial point. I mean, this is the starting point. And let's say that I go over the loop along this direction. Okay. Let's see. So that's the direction of the loop, and that's the starting point. So if I just write this expression as the sum of the potential changes, right? So basically, I start from here. In the first branch, I just go over this EMF device. So therefore, the change in my potential is basically my potential increases. And so therefore, this is E1. By the way, there are these other parts of that circuit that I didn't draw, all right? So just think of it like this. So as a result, this current and this current are not, may not be related with each other, right? Think of it like this. I'm just drawing some part of the loop in here. So what was I saying? So I'm actually writing the changes in the potential. So in the first branch, potential changes E1, so therefore I just write E1. In the second branch, you can think of it like this. If I1 is positive, then when I go along this direction, the potential really drops. So therefore, the change in the potential is equal to minus I1 R1. Okay? And on this branch now, again, think of it like this. If I2 is positive, in that case, this point is at a higher potential than this one. So when I go along this branch, then potential increases. So therefore, the change in the potential would be plus I2 R2. And then finally, when I go over this EMF device, the potential decreases. So therefore, change in potential is negative. Okay. And then say that this is equal to 0. So this is how you write down the loop rule, by using the change in potential concept, okay? But if I write this thing down in terms of the potential drop, I'm just going to basically add -1 to each term. So I'm going to write down the same equation, but this time I'm thinking like this. So let's say it like this. I think I'm going to use a pink color in here. So if I go like that over this branch, potential increases. So therefore, the drop is negative. So the first term is minus E1. If I go over the resistor, the potential actually drops. If the current I1 is positive, I don't need to consider any other sign, because I need to write this thing down in an expression in here, which is either plus I1 R1 or minus I1 R1. And I would like to understand what the sign in front is. In any case, here the potential really drops if I1 is positive, so therefore the potential drop is positive. In the third term, well, the potential basically drops if you move opposite. So that means in the direction that you are moving, the potential actually increases, so therefore the drop is negative. And finally, in here, the potential drop is basically potential really drops. And so therefore, this is plus E2. I think this is E2, right? Let me correct this. Okay. Actually, it's the same equation, but I just wrote this in a different way, okay? So these are the ones that you should be using. I don't know which one. You will be comfortable in one of them and not the other one. So as a result, I suggest that you follow the one that you are comfortable with. There will be some situations, there will be some circuits which are kind of harder to analyze. Not the DC circuits, but the circuits where there are like capacitors and other circuit elements, like inductors and things like that. In this case, I mean, whenever you're confused, I think this is the best way to write the circuit equation. And you know, for each element what the potential difference across the terminals is in terms of the other variables. You know how to express them. And so as a result, always use the basic step in here if you're confused. Otherwise, if you're not, then you can use the other methods. The one that I use in classes is basically can be written like this. I just write down, I mean, if there are only just EMF devices and resistors, so it's just the sum over the EMFs. Sorry about this. Is equal to, basically, I just write it down like that. So this is basically equal to the sum of the changes in the potentials when you go over the EMFs, and that's the sum of the potential drops on the resistors. So let me write it down like that, okay? So that's the sum of potential changes on EMF devices. And this is basically the sum of potential drops on resistors. Why do I use changes in here and drops in here? Because if I move this to the other side, for example, I will have just the sum of potential drops in here on resistors and EMF devices. Right? Think of it like that. In any case, if you don't want to use too many negative signs in your equations, you can always think of it like that. So you basically go over the loop and then write down these equations like this. So I'm just going to write this final thing in here. So for this, I think I'm going to use a green color. So again, I'm going over this loop, right? It's along this direction. But in the first pass, I basically sum over the EMFs. And in the second pass, I just sum over the potential drops on the resistors. So in the sum over the EMFs, this EMF has the same polarity as the direction that I'm moving. So therefore, this has a positive value. This is opposite to the direction that I'm moving. So therefore, I'm going to write this one as with a negative sign. So as a result, the sum of the EMFs would be E1 minus E2. Okay? And for the potential drops, when I go over this first resistor, I'm moving in the same direction as the current variable in here, I1. And again, if I1 is positive, the potential drop is positive. So that means if I'm moving along the same direction as the current, I always write down the term as with a positive coefficient, because the potential really drops there if the variable is really positive. And when I'm moving over this, I know that the current is in the opposite direction, so therefore the potential drop has a negative sign. Okay? So that's basically how I write this thing down. If there are just EMF devices and the resistors. For the other ones, well, I essentially use this one, right? Because I'm always confused about the signs and things like that. So as a result, I always go to the most basic form. Okay, I don't know if you have any questions in here, but as I said, I always use this in this form. Okay, so as a result, if you have some kind of a circuit like this, I don't know, let's say it like that, right? There's some kind of a circuit like this. Okay, so there's the number of loops in here. Think of it like this. Why is this important? There are actually, I mean, this kind of counting gives you the idea of how many variables you need to use and things like that. So for example, this loop has like these 3 eyes. So that essentially means that there are actually at least 3 loops that you need to write down the loop rule, right? So that means 3 loop rule equations. So I know that some of you will protest. So, I mean, these are not the only loops in here. So for example, sorry about this. So let me, yeah, use this color in here. So there's this loop as well. And you can even make this complicated. I don't know. You can take this loop as well. There are infinitely many ways. It's not infinitely. There are many different ways of actually choosing the loops. But it turns out that, for example, the loop rule for this loop, the loop rule equation for that loop, appears to be just the sum of the loop rule equations for this loop and that loop, right? So as a result, if you just consider all of these alternative loops, it's just going to be a repetition of these three loop rule equations, okay? So the number of equations that you can write down in here is equal to 3 because there are 3 loops in here. What about the junctions? I have this, that, and that junction. So if there's no junction, the current value is going to be the same on that branch. So as a result, you are going to use a single current variable in there. So as a result, there are these 4 junctions in here, number of junctions is 4, but it appears that one of them is, I mean, the junction rule equation for one of them is just a is just the sum of all the other ones. So it's something that can be derived. And so as a result, there are actually 3 junction equations, junction rule equations. Okay, so let me say it like this. One of the junction rule equation is, let me say it like this, can be obtained from others. Okay, we don't want to write down the all possible equations. We would like to write down the minimum possible equations, independent equations that gives us the essential relationships between the variables, right? So this kind of counting is kind of important. So it also tells you how we can choose the variables, right? So there are these tactics in here. There are many tactics actually, right? Basically, let me say it like this, choose variables such that either the junction rule or the loop rule is already satisfied. It's automatically satisfied. What does that mean? So this means something like this. So for example, for this kind of a circuit, let's say that you just choose some kind of a current variable in here. Let's say that you just call this as I1. And then let's say that you choose this current as I2. In this case, you just write down the value of that current as I1 minus I2. And so as a result, once you choose the current variable in here like that, you know that the junction rule at that junction is automatically satisfied, okay? So in any case, so you just choose the current in here as I3. And so to make sure that the junction rule is satisfied at that junction, you just choose the variable in here as I2 plus I3. And what else? So in this branch, for example, then the current would be I1 minus I2 minus I3, right? In any case, so in that case, that junction rule will also be satisfied. So you can check this last one by yourself. You will see that the junction rule in there is also satisfied as well. So that means junction rule is satisfied, which means write three loop rule equations. And of course, there are three unknowns, which are basically I1, I2, and I3. Okay, so that's one of the things. Basically, the number of unknowns should be equal to the number of the equations that you write down, because that's basically for all the problems that can be solved, right? So if these two numbers are different, then that means you're in trouble, usually. So as a result, it's not surprising that there are three unknowns in here, and so therefore there are three variables. A second possibility is this is the same kind of a circuit again, but this time, yeah, there are some nice tricks that people use to choose these variables in here, but I don't want to describe these kind of things. You're going to learn these kind of tricks later. So basically, you attach some kind of a current variable to, for each loop and do it like this. But in any case, that's something that I don't want to describe in here. Another possibility is to choose, for example, the potentials at some special points. In that case, of course, the number of variables may actually depend on what is on that branch. So I don't know, if there's some kind of an EMF device in here, for example, you may want to choose the potential variables somewhere in here. But in any case, I'm just going to assume some kind of the simplest possible situation. Let's say that on each branch in here, there's just only one device, let's say. So in that case, what you do is you just choose the value of the potential at certain points on the circuit. So usually these are at the junctions. But let me start with this. So the potential variable. So you always choose the potential value of some reference point to be equal to 0. You have this freedom in here. So you just choose an arbitrary point on the circuit and then set the value of the potential there to be equal to 0. And then use the values of the potentials at some special points as some variables in here. So this is like, this is V1, this is V2, let's say, this is V3, for example. If I assume that there's just a single thing in here, I don't know. So as a result, in that case, if you use these variables, in that case, the loop rule is already satisfied. So that's something that you don't need to check. Loop rule is satisfied. And what happens is that, for example, then you can write down the junction rule, right? Again, in that case, it is 3. So I think this is an accident. Write 3 junction rule equations. Etc. All right. But if there are some other points in here where you also assign a potential value, then you have to write down the junction rule for that junction as well. You have to somehow equate these two currents to each other, right? So as a result, the number of equations in here does not need to be equal to 3. It just turns out that, at least in the example that I have shown in here, it appears to be equal to 3. Okay. So in that case, the loop rule is satisfied. You just write down the junction rule. So we always do it like this, right? But this is by far the most common method, as I have seen. There might be some circuits where one method is more complicated than the other one. So as a result, it should be wise to be on the lookout. So I think in the problems that I have solved last year, I have shown both of these two methods for the same circuit. So as a result, I'm not I'm not going to do that here. Okay. What I do is I just solve this example in here. Unfortunately, it's the same example. So you're going to find the same circuit, solved again, but this time probably with different numerical values. The circuit has just two loops. This is a very simple circuit. Again, we don't have any reason to solve complicated circuit problems in here. And most of my circuits will have only two loops. So I'll call this as R1, this as R2, and this is R3. And I just choose them wisely. So yeah, I call R1 to be equal to this is 3 ohms. Yeah, there's a special reason why I choose them like that. So this R3 is 3 ohms. No, I'm sorry. Yeah, let me choose this as like, let me think about this for a moment. This is, yeah, I think I'm going to choose this one as 3, but in that case, the circuit would be simpler. 5. So let's say that this is E1 is 5 volts and E2 is 20 volts. Yeah, I think with that, the numbers will come out correctly, right? So I'm just going to illustrate the point in here. So I think the easiest way is to use the second method in here. So if I choose the potential variables like that, where the potential is 0 in here, then I know that the potential at that point is 5 volts, and the potential at that point is 20 volts. And so therefore, I need to use the potential at this point as a single variable. So as a result, this is kind of the simplest way to solve this problem. So let me solve it like this, right? So as a result, I mean, I'm just going to use this picture in here. So V is the only unknown in here. So as a result, I need to write down a single equation to solve this single unknown. And that single equation is basically junction rule. And I know that this point is a junction and that point is a junction. So I can use either one of them. Both of them is going to give me the same equation, but perhaps with different signs, right? So I'm just going to do it like this. So I think I'm going to use blue colors in here to distinguish things. So I'm going to call the current in here as I1, the current in here as I2, and the current in here as I3. Okay. So I don't know if these are really positive, but some of them can be negative. But in any case, when I write down the junction rule, I don't care whether these variables are really positive or negative. I just look what I see and then write down the equation, okay? So I'm just going to write down the junction rule in a moment. Yeah, in any case, so the junction rule says that I1 plus I2 should be equal to I3, right? So, but what I do is I express I1, I2, and I3 in terms of this unknown in here, and then insert into that equation, okay? So let's do that. I think I'm going to just slightly slide in here. So I'll start with the I1. So in that case, the potential drop in here is, when I go along the arrow, the potential drop is, just keep in mind that the potential really drops if this V is smaller than 5 volts. So let's say it like this. This is the potential drop divided by the resistance. So how do I decide on the sign? I go along the arrow in which the current is measured, right? So the amount of the potential drop in here is basically this potential minus that. So that's 5 minus V. So I'm not going to write down the units in here to make things simpler, right? So this I2 in here, it is this one. Again, the potential drops if this 20 volts is bigger than V. So therefore, this is 20 minus V divided by R2. And finally, in here, the I3 is, if I move along the arrow, the potential drop is V minus 0 and divided by R3. Okay, so as a result, when I write down the junction rule, I write it down like that. This is 5 minus V divided by R1. What's R1? That's 3. So let me write down the values in here. I2 is 20 minus V divided by 3. And I3 is V minus 0 divided by 6. I just need to solve this equation. Okay, on the left-hand side, I have like 25 minus 2V divided by 3. On the right-hand side, I have V divided by 6. So we have 50 minus 4V. That's equal to V. And so this is 5V is equal to 50. So that means V is equal to 10 volts. All right, so that unknown potential, therefore, at this point appears to be equal to 10 volts. Only with that value, the junction rule is satisfied. Okay, so by using that 10 volts, I can then determine all the current values. So I1 in here turns out to be minus 5 over 3 yeah, the numbers didn't turn out to be right for the current, but in any case, so it's just a value, right? That's minus 1.6, let me say 1.7 amperes. So this is 10 divided by R2, so that's 10 over 3. So that means this is like 3.3 amperes. And I3 is equal to 10 over 6. That's 5 over 3, so that also is equal to 1.7 amperes. Okay, so in any case, so we have a situation in here where I don't want to erase this picture and I don't want to redraw this thing either again. But in any case, I have just chosen some arrows and assigned variable values to it, right? So when I was drawing these arrows and assigning these names, I didn't know if the I1 will turn out to be positive or negative, or I2. And in this special case, it turns out that I1 is negative. Is this something wrong? Did I do something wrong? And the answer is no, because I didn't know that this point has a higher potential than this one. If I knew, then I would probably have chosen the arrow in the opposite direction. But this is okay too, right? The current can be negative, no problem with this. And the junction rule is satisfied, right? You can easily check that this is the case. I can easily show that I1 plus I2 is equal to I3 because minus 1.7 and 3.3 added up is going to give me 1.7. This checks up. No problem with this, right? So as a result, everything is okay actually. The only thing that's not okay is my being uncomfortable, but that's no concern for, I mean, that's not important for the physics part in here, right? So as a result, if it turns out that the current is negative, just don't 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 change the directions and signs after you solve the problem, right? Because this creates more complications. So that's perfectly okay. So you just need to interpret this in the correct way. And you can always use negative current variables. No problem with this. When you're writing down the equations, it's not going to be an important point, actually. Okay. So as a result, in here too, I don't, after solving the problem, I don't change the directions and solve it again. This is not needed. I don't even change the directions. This is perfectly okay for me. Now, what I'm going to do in here is to show the conservation of energy. So I think I'm going to magnify, use a smaller magnification here. So it's the conservation of energy. Which means energy produced is equal to the energy consumed, right? The energy is produced by the EMF devices. It is consumed by the resistors. How do they consume them? The resistors basically convert the energy into heat. Okay, let's start with the. I think the resistors. So the power of energy consumed at the first resistor is basically I1 squared times R1. And that's the point where it became important that I chose the variables in the correct way. Unfortunately, I didn't choose it like this, but in any case, I'm just going to do the calculation like this. So what was I1 again? So it was 5/3. So let me just do the calculation like this. So that's like, it doesn't matter whether this is negative or not. I'm taking a square. So this power is always positive. So this is going to be 25/3. So that's 8.3 watts. Power consumed on R2 is I2 squared R2. What was I2? This 3.3. I think this is 10/3. So that's basically 100 divided by 3. So it's 11.3 watts. And power consumed on the third resistor, I3 squared and R2. So this is 5/3, 25/9, and this is 50/3. Sorry about this. Let me check this again. I don't want to make a mistake in here. So this is 5/3. Square is 25/9. This is 6 ohms. So that's 50/3 watts, right? So that's 48, 51. Yeah, that's the difficult, it's a difficult calculation for me. So I think this is 16.6 watts. So if I add them up, let's say it like this, the power consumed is equal to 175 divided by 3. That's not helpful either. So let me say it like this. This is 27 plus 8, 35. I have one more 36, so that's 36.3 watts. Okay. So at the end, of course, it will turn out that the power produced will be exactly the same. Unfortunately, it's not unfortunate, it is fortunate. The power produced by the first EMF device, All right, it is given by this formula in here, but the current is minus 5/3 amperes, and the EMF is 5 volts. So as a result, this is minus 25/3 watts. So the power produced in that case by the EMF device is negative. So that's minus 8.3 watts. And the question is, what does that mean? Well, it basically means that this EMF device is providing a negative energy to the circuit. You can interpret it in the other way around. The circuit is giving positive energy to that EMF device. So essentially, we are charging that EMF device. So you can think of it as some kind of a charger circuit. So I'm using some battery to charge up that battery. Right? You can think of it like this. In any case, let's just continue. Power consumed on the other, power produced by the other EMF device is I2E2. I2 was equal to 10/3, and that EMF was equal to 20. So that's therefore 200 divided by 3. I also have to divide this. All right, so this is 180 plus 180. So let me write it down like that. This is 18 plus 2. Sorry about this. I cannot do this in the usual way that you do. So this is 66.6 watts. So the total produced is basically computed in the same way. I just need to add these things up. 66.6 minus 8.3. And I get, I know that I get 0.3, but this is 54, 58.
Hocam, PR2 is wrong. 100 and divided 3 must be 32.2, 33.3, like this.
Which one?
PR2 on the top of this, the resistor part.
This
yes,
one?
This one, yes.
What is this? This is 90, that's 33, sorry about that. Right, let's just do this part again, all right. This is 24, 54, 57, 58. I'm sure that this is also 58, so let me just pretend that it is 58. But in any case, I mean, power consumed is equal to the power produced, so therefore the energy is conserved. So we are happy that the energy is conserved at the end. Okay. So in any case, let me stop here. If you have any questions, then you can ask me in the break.